Hello, math fans and family. I'm a longtime professor at the University of Washington. I teach big calculus classes, and I've been making videos like this just for fun to talk about problems I found interesting over the years and to give me a little release. This video is going to be about how to spread your family out at Thanksgiving. So this is a problem I've thought about for years, off and on. Never really have solved it. So I'm presenting this as an unsolved problem for you, but I'm framing it in the form of, we're about to have Thanksgiving when I'm making this video. We just had a contentious election. You might not want to sit very close to your uncle or your brother or your sister. You might need to make sure your divorced parents aren't sitting next to each other. Maybe you have an uncle that always tells your kids how big they're getting and your kids are annoyed. My son said, maybe you have somebody that always eats too many beans and doesn't smell very good. So we would like to spread people out. Now, this actually is in honor of my family. I love them so much. We have a family. I like to sit next to them. We have great family traditions. There was one year where my uncle, who was very old, we were passing the turkey around and he sneezed, achoo, right on the turkey. My brother's like, okay, I think I'm good. So our family has a great time together. We sit close, but imagine you wanted to sit far apart. Okay, here's the real story. When I for years I teach these large calculus classes. I found this is a seating chart I made for one of my final exams. Sometimes I have 400 people in a room and I'm giving a final. It takes a lot of thought on how to spread people out. What's weird at the University of Washington is a lot of our rooms don't even have seat numbers, and so I have to make a map. I have to figure out which seats are left-handed seats, and then I assign students so that they're somewhat spread out, just to give them more space and try to avoid cheating, all that fun stuff. But every time I proctor these finals, they take 3 hours. I always think about, what if you had total freedom, you had a large space, and you wanted to spread people out as much as possible? How could you do it? Now, in my case, we can't spread them out very much. But that got me thinking about this problem, and I would only think about it during my final exam. So 3 times a year, I would think about this problem. After a few years, I started to write some notes. And then at one point, I started to tell my TAs. Okay? And then after about 10 years of this, I finally searched it up online. And sadly, I found that it's equivalent to a problem people had already done. I was sad. I was hoping I had thought about my own problem. So we are going to do this. We're going to pretend it's Thanksgiving. And we're going to get a very large room, square room. We're going to make it 100 feet by 100 feet. My son was like, you're getting a hanger or something? And we're going to spread them out. Now, if you only have 2 people, you're going to put 1 chair over here and 1 chair over here. This is the antisocial Thanksgiving. And the distance between them, and I'm going to do a few examples, basically 1 through 6. It already gets hard then. And so if you have more than 6 people at your Thanksgiving, this is not going to help you. But I think it introduces some interesting math. It shows you a famous, hard, unsolved problem. Anyways, fun little bit of Pythagoras here. We have a triangle. A squared plus b squared is c squared. Every year when I would be drawing up the baseball fields in our baseball league, somebody would come over and ask me the Pythagorean theorem, so we knew how far it was from first to second. Anyways, this is going to be, I'm going to do a few calculations here. Apologies if I've already lost you. But that's going to be this plus this, and then we're going to hit that square root button. So C is going to be the square root. And I'd like to know these distances. Okay, and I picked 100. Normally when we would do this, I would just pick the number 1. But let's do the square root of 100 squared. I'm going to use an online calculator so you can see what I'm doing. And I get 100 squared root of 2, it's 141. It's not a nice number. It's an irrational number, 141.42. So 141.42. We'll round things here. That's the best you can do. That's the farthest you can get them apart. I believe that one's true. And I'm going to make some claims in this video, and they may not be true, and I would love for you to post something that disproves me or comes up with a better solution. Like I said, I only would allow myself to think about this 3 times a year. Okay, so now you get 3 people. And we're just trying to build up. This is how we do math. We sort of do basic examples. So this is the furthest apart I can get them, these 2 people. So here you have your divorced parents that have to sit across the way. Okay, now you want to spread out 3 people. And you should experiment on your own. It's a fun little game you can play. You know, what if you put them here? Well, then you'd have a couple people that are 100 feet apart. And you're like, well, then maybe that's good enough. Maybe that's not good enough. Maybe I want to spread them out a little more. And I remember I used to think about this and I bet, oh yeah, you could do quite a bit better. What if you did something like this? Then the minimum distance is going to be more than 100 feet. Now, if you're trying to keep those 2 people apart, you have to spread them out as well. So I remember thinking, what if I made this an equilateral triangle? These were my first thoughts. Later I can't even find my notes. This was so many years ago. I've been teaching for 20 years. This was like my first 10 years. It's just popped into my head. And so I'm reviving it. I never got to publish it. I never proved anything. Maybe one of you will. But I'm just glad that the problem gets to live on. So I think I labeled that C, and then I solved for C. I used the fact that I think each one of these angles, if it's an equilateral triangle, is 60 degrees. I did some stuff. All right, I figured out that's 90 degrees. So I'm going to have these have to be 15 degrees. And for those of you that are math people, I think I used the fact that I knew this side, and I wanted this side, and I knew the angle. And so I think I said cosine of 15 degrees. And if you're not math people, you can go to sleep now. 100 over C. And I got C was 100 over cosine of 15. So there, already getting to do some work. 100 over cosine of 15. Got to be careful using an online calculator because it's going to be in radians. Cosine of 15. I don't know if I can write it this way. I could convert it as well, but let's see what it does. 103. 103.53. 103.53 feet. That's slightly better. This is like 26 feet. I think I did this calculation before. I wrote it down somewhere, but this video is already going to be too long. Okay, so that's the best you can do with 3 people. Person 1, you have to sit here. Person 2, you have to sit here. We don't like each other in this family. We want to be far apart. Okay, with 4 people, I'm fairly convinced you're going to sit them all in the corners. So with 4 people, we're going to have you sit in the corners, and the distance is going to be 100 feet. Now, some of them are going to be more than 100 feet apart. That's a bonus for them. But what I'm asking is the minimum distance. Can we maximize the minimum distance between them? So far, our little table, if we were going to make a table, this is what we would do in math. We would say, well, if there's 2 people, if there's 3 people, if there's 4 people, what, darn it, sorry about that. I'm going to do it again. What is the minimum distance? So you can get them within 100, you can spread them out this far. With 3 people, you can spread them up to 103.53 feet apart. With 4 people, you can get them 100 feet apart. Okay, what about 5 people? Then things get a little more interesting and harder. And I remember over the years thinking, again, I'd only think for these 3 hours on this problem. What if we put a pentagon in there and equally spread them out just like we do with a triangle? Oh, I made a nicer picture of the triangle because I knew I would do a bad job of drawing it. There's a precise... Ooh, I did pretty darn good. I guess I didn't need that. Maybe I could impose it on there. Come on. This is a huge waste of time. You say we stopped watching. No one is watching at this point, so it doesn't matter what you do. Okay, here we go. So we want this distance. We're going to go here. And so I figured out, well, if you could figure out a regular pentagon in there, I think this had to be, let's see, that has to be 72 degrees. If that's 72 degrees and this is 90 degrees, this has to be 18 degrees. Does that add up? I wrote this down somewhere. I thought I'd be able to recall it as I was doing these problems. So if this is 108 degrees and this is 18 degrees, I'm trying to see if I can find my notes where I wrote this down. You didn't prepare? No, this is what I do. Anyways, that's going to be 72, 18. Oh, I think I did this in a longer way, but let's keep going. So what would be 108 plus 18? So that's 126. And all three of those angles should add up to 180. So I'm doing a bit of angle work. And I had to think about this. And I'm, like I said, the video is already too long, so I'm not going into all the detail. But that's going to be 54 degrees. Okay. And if that's 54 degrees, and this, I'm probably making a mistake somewhere in here. The point of the video is this idea. So let's see this. And I'm jumping a little bit. But 108 degrees is what one angle in a regular pentagon are. I think 72 is right. Let's do some checking. Minus, that's 18. I'm confident in that. So we did 108 plus 18. And then we subtracted that from 180. Don't forget those parentheses. 54. So now I would like to do 90 minus 54. And you're probably wondering, why is he calculating all these angles? I'm trying to get it down to a triangle where I know some of the sides. And so this is 36. And so I have this triangle. I know this is 50 if we're doing this 100 by 100 room. And so finally, after a lot of maneuvering, and that's not the way I originally solved it. I'm hiding a little bit of all the effort that went in. In fact, I didn't even need to find the 36. What a huge waste of time. 54 degrees, this is C. So sine of 54 degrees is 50 over C. And this is often how it goes with these trig problems, that if you think about it long enough, you can find a much shorter way, but your first effort takes forever. So we're going to do 50 over sine of 54 degrees. Sorry, my penmanship is bad over there. 50 over sine of 54, and we want that in degrees. 61 feet. So that's a very dramatic change, and apologies if I made any mistake along there. But what I remember thinking was, well, I can do better than 61 feet maybe by doing the following. Taking the 5 people, putting 4 in the corner and 1 in the middle. And if you do that, this will be the minimum distance between them. And that's going to be half of that first number, which is way bigger than 61. So what you find out is that all that was a huge waste of time. But it was good to sort of consider. That's not the best answer. I think this is the best answer. Maybe it's not. Maybe there's another answer. In which case, the best answer for this is to spread them out as follows. You say, you 4 go in the corners. And then one of you sit in the middle. I don't know who's the unlucky one in the middle. Whoever everyone likes the least gets to sit in the middle. And that's going to be half of that number from earlier. Maybe I can just grab it. Here we go. We're going to do half of this. Ta-da! Let's see what happens. 70 feet. So this was not optimal. And as a mathematician, I don't like that. I want to prove things optimally. And so because of that, I never told anyone about the story. I felt sad about myself that I couldn't find the best answer. Now that I get older, I realize I have almost no answers. And I'm much more interested in just giving other people these problems. Okay, so here we go. One last one. What if we try to do a hexagon? Now, I know this is not optimal. I did this already. I found that this was 60 degrees, and then I solved for this, and I did this, and it was like 52 feet for this length. And I knew that wasn't optimal. So what is optimal? I think this is optimal. And then I started to go, well, where would I put those 2 points in the middle? And so I started to play around with this, and this is about where I stopped. This is the year that I looked things up. Every year I would add a little dimension to my thinking here. And I said, well, what if you could put those right in the middle and make all of these have the same length? And at some point I realized, well, I could label it a little more, kind of break it down and say, this is C, this is C, this is C, dot, 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 doop, 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 this is C. The little length here is going to have to be, those two things added together are going to have to be 100 minus C. So each one is going to be 100 minus C over 2. That was my thought process. And then I knew this was 50 because it was halfway down, and that gave me a triangle. And I did all this today with my son. He helped me, my 12-year-old son. I made him draw several of these, and I was like, will you just be my sounding board? Because I can't find my research on this as I thought about it over the years because it's scattered. Okay, so then I have a right triangle, Pythagorean theorem, 50 squared, 100 minus C over 2. And at this point you're thinking, what a huge waste of time, you weirdo. Oh well. Like I said, I just thought about it. I didn't do research. I was trying to teach students. Okay. This is a quadratic equation. Normally I'd expand it out and sing the quadratic formula for you, but since this is a video and you're already asleep and no one's still watching, we are going to do this. So we're going to do 2500 plus 100 minus C over 2. Darn parentheses. You get to hear my typing because I'm not good with audio. You got to ask my other brother who's very good with audio and video. He's saying, what is this guy doing? And we're going to solve this. Ooh, why did I do that? I want to solve it. It's a quadratic formula. You get this 100 over 3 square root of 7 minus 1. There's two answers, but one's negative. And so this gives me 54.86 feet. So we're doing 54.86 feet. 54.86 feet. And that's a little better than doing this thing here. I think this is about 52 feet. That's only up to 6. I haven't even gotten to your Thanksgiving party yet. As soon as you have 7 or 8 or 9, I don't know the answer of how to spread people out. So at some point after I thought about this for a few years and I told TAs and I've run out of interesting ideas, I was like, okay, I'll finally search it up. And sadly, I found, I don't know if it's sad or happy, I found this problem called circle packing. Circle packing is trying to fit circles into a rectangle. And they did this equivalent, and then I read, equivalently, the problem is to arrange endpoints in a unit square aiming to get the greatest minimal separation. And I was like, oh, that's my question that I thought I invented. I did not invent it. It's been studied a lot. Circle packing is kind of notoriously a hard question. You can talk about the optimal way to pack circles. Oops, that's this one. Packing problem. And, you know, whether you pack them like this or you pack them every other, people have studied this a lot. This is kind of an optimal way to pack circles. You can think of it in 3D even, like when you're trying to put tennis balls in a bin. I play a lot of tennis. A lot of interest in this. If you start to ask specific questions of what's the radius that best fits, it becomes a lot harder. So people have done this, and so you can imagine the people are the center of these circles, and there's that solution I talked about. Cat's trying to escape. Here's the second solution I talked about, if people were in the center. The reason it's equivalent is because the circle is like the distance away from them. So it's kind of like a radar screen. I don't want anyone in my region, anyone in my space. Here's the solution for 5. My solution for 6 is wrong. It says the optimal solution is to do this. Oh my gosh, I didn't even realize that until I was making the video. But that makes it even better. So it's saying that this 54 feet is wrong. I don't know why I take joy in being wrong now. I feel like people are so so stuffy in math sometimes that they have to be right, and when they're wrong, they're trying to defend themselves. So I cannot defend myself. I'm not right. It says that we should put them like this, in some way. So my solution was not right. We would have had an aunt and an uncle or people sitting closer together than we want. So that's very funny to me. So what did I get? And they do a radius of 1, so the numbers I'd have to rescale, but that wasn't optimal. Look at that. It says for 7, you should put the people like this. For 8, you should put the people like this. For 9, that maybe makes sense. And you can see it goes on. It says that shown solutions not necessarily optimal. That's what I mean by it's an unsolved problem. For several of these, it says solutions for everything up to 10,000 have been found, but they're not necessarily optimal. Up to 20 is shown below. So it's an unsolved problem. It's just hard to figure out the best way to configure. I always found that interesting. I hope you gained something from this video. And to my family, I do want to sit close to you. We're going to pack us in a little closer. The truth is, in our family, you have a giant house, and then you have this one room where the food is, and everyone sits in that room because we like to eat. All right, love you, family. I hope if someone has an interesting idea about this problem, it'd be fun to do a little project. I'm less interested in circle packing and more interested in spreading people out.